Kia ora koutou, welcome to this video, which is the fourth video of bonding and structure, and hopefully the last. So in this video we are going to be talking about polarity. We've mentioned polarity before in previous videos when we've talked about the solubility of ionic compounds. So remember we had ionic compounds such as salt, which have positive ions and negative ions, are soluble in water, and that is because water is polar, so it has a negative part to it and a positive part. But when we're talking about polar molecules, we're talking about slight charge. So if we were to show those slight charges on water, we would draw oxygen covalently bonded to two hydrogens, and the slight charges are on each of the atoms. So each hydrogen has a slightly positive charge, and the oxygen has a slightly negative charge. So we show slightly with this symbol delta. So give this some practice drawing that. You just need to copy how I'm doing it here. So we've got slightly positive and slightly negative charges. When ionic compounds dissolve in water, the slight positive charges are attracted to the negative ions in the ionic compounds, and the slight negative charges are attracted to the positive charges, the positive ions in the ionic compound. Today, for this video, we're going to be looking at why there are these slight charges. So the first concept we need to know when we're learning how to explain this polarity of this molecule is electronegativity. So electronegativity is the tendency of an atom to attract shared electrons towards itself. So that means that an atom that is more electronegative than another atom will have a stronger pull on the electrons if they had a covalent bond. So remember, covalent bonds are bonds where electrons are shared, and if the bond is between two different types of atoms or two different elements, then the element that has the greater electronegativity will pull the electrons more than the atom that has the lesser electronegativity. So there's a way of knowing which atom in a bond will have the greater electronegativity as an approximation. So atoms to the left of the periodic table have a lower electronegativity, and atoms to the bottom of the periodic table have a lower electronegativity. So as we go from left to right on the periodic table, excluding group 18, we're just looking at groups 1 to 17. So as we go from left to right, we have a greater electronegativity. And as we go from the bottom to top, we have a greater electronegativity as well. So that means that fluorine has the highest electronegativity of all of the atoms. So let's think about water. So the bonds that we have in water are between an oxygen atom and a hydrogen atom. So oxygen is far further right on the periodic table. So we can say that oxygen has a greater electronegativity than hydrogen does. So we'll just draw one of the bonds that we would see within water. So oxygen here has the greater electronegativity, so it's going to pull electrons more than the hydrogen is. So the electrons are going to spend more time around the oxygen atom than they will around the hydrogen atom. And so if we think of electrons, what charge do electrons have? Electrons have got a negative charge. So if electrons are spending the majority of their time around this atom, then this atom is going to have a slightly negative charge. So oxygen has a slightly negative charge, and the hydrogen, this is not going to have electrons around it as often. So what that's going to do is it's going to expose the nucleus of hydrogen, and in the nucleus of any atom is positive charges with protons. So here the protons are going to be more exposed, or the one proton in hydrogen. So that's why the proton will give this side of the molecule a slightly positive charge. The bond like this one between atoms that have different electronegativities is what is called a polar bond. So anytime there is a covalent bond between two atoms that have different electronegativities, that bond will be a polar bond. For this course, for Structure and Bonding Level 2 NCEA, we assume that every different atom has a different electronegativity. So whenever you see two different atoms bonded together with a covalent bond, we can say that that is going to be a polar bond. So we don't actually need to know how great the difference is in electronegativities, and in fact, we don't even need to know which one is going to be more electronegative, except for water. We need to remember that oxygen is more electronegative than water for when we're showing that an ionic compound is soluble. Apart from that, we don't need to guess which atom has got the greater electronegativity. So we don't need to show where these charges are. This idea of electronegativity is just to give some context to what we're about to explain, which is a polar molecule. So it is important to know that whenever there are two different atoms bonded together with a covalent bond, that bond is going to be a polar bond. To work out whether or not a molecule will be polar overall, we need to combine the knowledge of whether or not it contains polar bonds with whether or not the molecule is symmetrical. So symmetry, we might think that that's quite an easy concept. If you can draw a line of symmetry and fold a shape over itself, then it is symmetrical. For this chemistry purpose, we kind of need to use a slightly different definition of what symmetrical actually is. So we'll have a look at different shapes that we've gone over before. So this is the table that we went over in the previous video. So before it was a lot messier. I've just redrawn it. So if you want to, if you don't have this in your notes already, I would recommend writing this down. These are really good notes to have. So I'll just hover over here for a while for you to be able to look at, and then I'll scroll down. So you could pause it on this and copy these notes. And then the remaining two, you can copy these down as well. So what I've added into this table is whether or not the molecule is symmetrical. So when we're talking about symmetry in chemistry, we've always got the central atom. And so if we think about a symmetrical molecule, just pretend that there is a tug of war going on. So all of these hydrogens are competing against the central atom, or they're competing against each other. So these hydrogens are all tugging on their ropes, and if we think that the carbon would move overall, so if these hydrogens would be able to move the carbon, then that would be considered a non-symmetrical molecule, whereas if the carbon would stay in the same place, then that is a symmetrical molecule. So in this shape, this is a tetrahedral shape. So these are all arranged evenly around that carbon atom. And if there was a tug of war going on, the carbon would actually stay in the same place because the net pull of all of these hydrogens would be zero. They would all actually cancel each other out. So in this case, the carbon would stay in the same place, and this molecule would be non-symmetrical. Okay, so this one is non-symmetrical. So anytime you see a tetrahedral shape that has the same atoms, the same four atoms around it, that is going to be, oh sorry, did I say non-symmetrical? That is going to be a symmetrical shape. Now if we look at this trigonal pyramid, if you can imagine these hydrogens having a tug of war with the nitrogen, all of these hydrogens are pulling approximately in the downwards direction. So in this case, there would be an overall, this nitrogen would be moving in this tug of war. So this would be a non-symmetrical molecule. So for ammonia, for these trigonal pyramids are always non-symmetrical. a bent molecule. You can see from the shape here that if both of these fluorines had some rope and we're pulling the sulfur would be moving downwards towards them. The net pull would be downwards. There wouldn't be the net pulls would not cancel each other out. So in this case, this molecule is non-symmetrical as well. All right, if we look at beryllium trichloride, we've got these chlorine atoms. They're all arranged evenly around this beryllium central atom. So if they're the same deal, if there was a tug of war going on, all of the chlorines, the way that the direction that they're pulling would cancel each other out. So there would overall be no movement on this beryllium in the center. So this is actually a symmetrical molecule. So trigonal planars, if they've got the same atoms around the outside, that would be symmetrical. This one here, this is bent. This is the same shape as what we had here. So this one is actually, we don't need to go over this. This is non-symmetrical as well. And finally, we've got carbon dioxide. So if you've got a carbon in the middle and two oxygens directly opposite each other, and they're pulling with the same force, that carbon is not going to go anywhere. So this one, carbon dioxide, a linear molecule, is going to be symmetrical. So with these two concepts, the first one being symmetry of molecules and the second one being the polarity of bonds, we can decide whether or not a molecule overall is going to be polar. So what we need, the formula that we need to know for whether or not a molecule will be polar or non-polar is that polar molecules contain, I'll zoom in on this so you can read it, contain polar bonds and are non-symmetrical. Non-polar molecules they either contain polar bonds and are symmetrical, or have no polar bonds and they could be either symmetrical or non-symmetrical. So if a molecule has polar bonds and is non-symmetrical, then that is a polar molecule. If a molecule has polar bonds and is symmetrical, then that is a non-polar molecule. Or if it just has no polar bonds, then we can actually, well, it depends on how specific you want to be. If a molecule has got no polar bonds, then it will not be a polar molecule. So we'll go back through the examples and decide whether or not each of these are polar or non-polar. So methane, does this contain polar bonds? So if there is a covalent bond between two different atoms, then that is a polar bond. So these here are polar bonds. So we've ticked off the first part. Are there polar bonds? Yes. So it could be, if it is symmetrical, then it'll be non-polar. If it is non-symmetrical, then it will be polar. So we'll look at that structure there. That is a tetrahedral shape, and we've decided that that is a symmetrical shape. So if there are polar bonds, but the molecule is symmetrical, then the molecule is non-polar overall. So we'll write in the polarity of it. So is methane polar? No. Methane is non-polar overall. Okay, next one, we've got ammonia. So ammonia, we've got polar bonds because this is a bond between different atoms. So it does have polar bonds. The next question we need to ask is the molecule symmetrical? And we've worked out that ammonia is non-symmetrical. So if something has polar bonds and is non-symmetrical, then that is going to be a polar molecule overall. So in this case, ammonia is polar. Cool. Now this next one, we've got polar bonds because it's between fluorine and sulfur. The shape of the molecule is non-symmetrical. So if we've got polar bonds and the shape of the molecule is non-symmetrical, then the molecule is polar. Here we've got polar bonds, chlorine and beryllium. So polar bonds, is the molecule symmetrical? Yes, it is symmetrical. So that means that these dipoles or charges will cancel, and so we end up with a non-polar molecule. So that one would be non-polar. And we'll keep going. This one has polar bonds again, and it is non-symmetrical, so this molecule overall is polar. And then carbon dioxide, that has got polar bonds, but they are arranged symmetrically around the central atom, so this carbon dioxide is non-polar. Okay, so that is how to work out the polarity of a molecule. What's really important with this course is that we're able to write exam answers to be able to get the highest grade possible. So if you listen in on the next video, we'll go over some past exam answers and we'll look at a really good exam technique for these questions. There will always be a question about polarity and also shape of molecules in an exam. So it's really important to get good practice doing this. Thanks for watching this video. Like and subscribe for more chemistry videos. See you next time.